All right, so limits. So we talked about chapter 2, so now we're in chapter 4. Why are we coming back? Well, remember, what's chapter 4 about? Using derivatives, right? Using derivatives. Okay, well, we're going to learn, well, actually not till Monday, but we're going to learn about how a derivative can be involved in doing a limit. Okay? So we're going to get that Monday. But before we do that, we've got to review what we already know about limits, and we've got to add in infinity. We touched on infinity, but now we've got to talk more about infinity. Infinity is a thing that kind of can really be confusing. And did you know that there are infinite sizes of infinity? Yeah. There are different sizes of infinities. There are more rational numbers. Okay, what's a rational number? Well, let's say real numbers. There are more real numbers which are rational and irrational, like square root of 2, 1.414, right, is an irrational number. Doesn't repeat, doesn't terminate. Rational numbers are what? Non-decimal, well, no, that's irrational. Non-repeating, non-terminating. So rationals are, they either repeat or terminate. In other words, they can be written as a fraction, a ratio, which is why they're called rational numbers. They can be written as a ratio of P over Q, right? Any fraction is either of two whole numbers. Any fraction is either repeats or it terminates, right? So non-repeating, non-terminating, like pi, square root of 2, those are irrational. Okay, so there are more, and so those two together are the real numbers. So that's everything besides just I, for example, right? The complex numbers, okay, the imaginary numbers. So there are more real numbers between 0 and 1 than there are whole numbers. Whole numbers are 0, 1, 2, 3, 4, 5, on and on and on. Right? Now, I couldn't explain to you why. I could at one time, and I learned it in college, but there are more real numbers, decimals and so forth. Now, you say, how can that be? There's an infinite above, right? There's an infinite above. But, and I remember it had something to do with mapping. It had to do where you could map, so you could map a whole number like 0 to an infinite number of numbers inside between 0 and 1 and not hit them all. And then you could map, or you could pair 1 with an infinite number of numbers that were different than that other group of numbers. And then you could pair 2 with an infinite, I mean, it was crazy. So there were more numbers between 0 and 1, real numbers, than there are whole numbers. It's bizarre. So you start getting, that's when you start getting into number theory and stuff like that in college, and it's very theoretical and tough to grasp onto. So we're gonna get into this idea of infinity just here a little bit. So, matter of fact, this is probably as good a time as any to tell this story. So this was in that same class. This is the story I remember my college professor saying. He said, what's that? Well, I can't remember if this one was, there's one called number theory. And then we had another class in logic. And I don't remember the name of the course, but it was basically logic. It was some geometry stuff. And there was another problem I got from that I'm actually going to give you guys as a bonus later next semester. So it was one of those two classes. But this story has to do with the Infinity Hotel. So imagine you have a hotel that has an infinite number of rooms. Okay? And it's full. Okay? There's somebody in every room. Every room has a number. Room 1, room 2, room 3, room 4, on and on and on. And there's somebody in every room. And somebody comes to the hotel and wants a room. Can they fit him? Yeah. How? Well, that's really good. Couldn't everybody, now it'd be a pain, and why should you have to? But that's the way this hotel operates. everybody picks up their belongings and moves to a room that's one room higher than the room they're in. Couldn't everybody do that? Everybody can move to a room that's one room higher than the room they're in. And now, what do you got? Room 1 is empty. Because the person in room 1 moved to room 2. So room 1 is empty. So this person takes room 1. Okay, and so a group, a big group with 100 people, 100 different families, big, convention, I don't know, whatever, comes and they need rooms. They need 100 rooms. Could they fit it? Same deal. Everybody, get on the speaker, everybody move to a room that's 100 higher than the room you're in. So you might have to walk a ways, but everybody can do it, right? And there would be 100 empty rooms, and so on and so forth, just so you could do it, right? Then a really big convention comes to town, and they need an infinite number of rooms. And the guy says, no problem, we can do it. How's he do it? No. Infinity is not a number. Infinity is not a number. As a matter of fact, my high school teacher used to get up on his chair and say it over and over again. Infinity is not a number. Infinity is not a number. Infinity is not a number. You can kind of treat it as a number, sort of, kind of, but infinity is not a number. Could you do the same thing you did before? Could you get on the loudspeaker and say, everybody go to a room that's an infinite number higher than you were before? No. You never get there. But the guy says, yeah, we got you. We can do it. No. No. Everybody's got to be able to move to a different room that they can actually get to, a numbered room that they can get to, leaving an infinite number. Yeah, but you'd never get done doing it. Yeah, you say, okay, everybody move up one. Okay, now everybody move up another one. Now everybody move up another one, right? How long would you have to do that until you had an infinite number open? Forever, right? You can never do it. But you got to be able to just get everybody to move to a new room and open up an infinite number of rooms.
You just evict the current.
You say, hey, sorry guys. It isn't as hard as you think. But it's a little outside the box.
I think convention has infinity.
Well, it's a big number. Nothing? Yes.
Well, since the hotel is infinite, you have essentially a limitless number of rooms.
Right.
A limitless number of people in the rooms. You just add a second. If you have a second party of infinity, you will still have infinite rooms to fill. Right?
Well, but right now, every room has somebody in it. We need to open up an infinite number of those rooms.
You have infinite rooms.
Yeah, but somebody's in every room right now. Huh? Well, it could be one floor, one long floor. It could be go up, whatever. We got elevators,
It takes you an hour to get to.
It might take a while. In this particular scenario, it may take you a while, but they're fast. It's Star Trek. We transport, right?
What's the next deal with the station?
Even and odd.
I'm still confused about where they're.
Even and odd. Will's got it.
No, I don't.
You don't have it. Even and odd is what. There's your big hint.
Half the people,
Oh, that's really.
half people go to the square.
No, you have to go to the square.
The square room.
No, that's where even and odd. Everybody go to a room that is twice the number you're in right now.
So everybody's in.
So room 1 will go to 2, 2 would go to 4, 3 would go to 6, 4 would go to 8, 5 would go to 10. Now, if I'm in room 1,000,000, I've now got to go room 2,000,000, which might be a ways away, but like I say, we transport you. Think about it. Wouldn't that work? Everybody's in a room. Tell everybody to go to a room that's double. Couldn't they get there? Wouldn't there be a room for that person? There'd be a room for everybody, right? Everybody goes to a room that's double the number you're in right now. And what would be open? All the odd rooms would be open. And how many are there? There's an infinite number of odd rooms.
I would not go back.
So, yeah, they're not a great place to stay. You get woke up in the middle of the night, hey, everybody, you know. But just that alone blew my mind, right? It's full. There's somebody in every room. And we got an infinite number of people waiting outside, and everybody that's there, it's full. Everybody moves to a room that's double the one they're in, double the number they're in, and now half the rooms are empty. Half the rooms are empty because infinity is not a number. But all the odd rooms would be empty. And so those people get now fit in. That's what is just kind of crazy about the concept of infinity. And that's what infinity is more of a concept than it is a number, right? And so that's what we're going to really have to get our mind around as we talk about these limits. Okay, like x squared, right? We just know that those arrows go on forever. That's what we say, right? That's infinity. Okay. All right, so let's review where we're at. Whether you want to write, how much of this you want to write down, it's totally up to you. You might want to jot some of it down, but it'll go pretty quick here. So, but anyway, this is review. This is what we did before. So we talked about the cars meeting, all that stuff, right? So just a quick review. So if I say the limit as x equals -1, you would say what? What would be the limit as x approaches -1? Does not exist. Now, we're going to add something to this today so from now on, does not exist is not good enough as an answer by itself. Now, why is it does not exist? It's because the cars don't meet, right? If a limit exists, the cars meet at a number. A limit has to be a number. It has to be a number, and infinity's not a number. It has to be a number where the cars meet, an output, right? But if we get does not exist, and I let you get away with that on our last quiz, you just said does not exist, and that was good enough. If it does not exist, you got to tell me why it doesn't exist. Well, the reason it doesn't exist is the cars don't meet. Now, you can't say that, the cars don't meet. You got to say what is the limit on the left and what is the limit on the right. You got to show me why they don't meet. So in this problem, you would have to say x approaches -1 from the left is 2, and x approaches -1 from the right is 1. And you would have to add this to your answer. Okay, so let's be real clear about that. From now on, if the limit, so it's one of two choices. The limit either exists and you get a number answer, which is where the cars meet, or you get does not exist and you have to tell what happens on the left and what happens on the right. Okay? Now that one-sided limits will always exist from the left or the right. The cars are going somewhere. Now, I say that, it might be going to infinity. We're going to get into infinity today. The car might be going to infinity. But if it is, we'll just put infinity. Okay? All right. Still, on the one-sided limits, right? If both cars are going to infinity, we're going to talk about that. What if both cars are going to infinity? The limit doesn't exist because they're not meeting, but they are both going to infinity. So we'll say does not exist, and then we'll say the limit on the left and the limit on the right is infinity. Right? We'll say that. And you'll see that here in a minute. Okay, and we're starting with graphs because graphs were the easiest way to think of them because we could see them and we could think of the cars, but we're going to do mostly with equations. And so that's, I first want you to get the picture of it in your head, and then we'll do the other limits. Okay, what about the limit as x approaches 1? What's the limit as x approaches 1? -2. Right? Diner burned down, moved to a new place, we don't care. Right? Where do the cars meet? They meet at -2. The limit is -2. Now, don't confuse this with continuous, right? We talked about continuous functions. Is this function continuous here? Or no. Why is it discontinuous? We had 3 different reasons, right? One reason it's not continuous is the limit doesn't exist. Well, that's what's happening here. The limit doesn't exist. This is not continuous here. Well, why is this not continuous? The limit is -2. Well, not just because it's undefined. It's not undefined at that point because it's defined right here, right? At 1, we get an output of -1, but remember they got to be equal. Remember we had 3 things. The function has to be defined at that point, which is why 3 is no good, right? So it's discontinuous here because the function's not defined. It's no good here because the limit doesn't exist. And it's not continuous here because the limit is -2 and the output is -1. The limit doesn't equal the output, right? So these are 3 different points of discontinuity, right? But don't confuse that with limits, okay? Limits is where the cars meet. So Max, does that make sense? It's -2. The limit is -2. That's where the cars meet. What's the limit as x approaches 3? 1. The cars meet at 1. And of course, I just picked out the interesting points. What's the limit at 0? What's the limit as x approaches 0? Looks like about -1/2, right? I mean, that's just the cars meet there. But, you know, on a piece of the curve where there's nothing weird happening, it's just the output, right? So a lot of times, remember, what's the first thing we did in the limit problem when we had equations? First thing we did, if we had limit as x approaches 2 and then an equation, or an expression, not an equation, expression. You plug in a 2, you do direct substitution. So the first thing you do is plug in a 2 because a lot of times the limit is just the output, right? A lot of times the limit is just the output. So you always try that first because it might be that. But if something weird's going, now of course if you had a graph like this, you'd know it because it'd be a piecewise function, right? If you ever had a graph that was this, it'd be an easy equation to spot because it'd be a piecewise function, right? We're going to talk about equations that have asymptotes and stuff like that, and that's why we're going to get into infinity today, okay? So if you have a graph like this, it's going to be easy. If you have the equation of this function, it's going to be piecewise. So right away, you're going to know where the breaks are. You're going to know, remember we did that, you know, when it switches from one graph to another, that's where those breaks are going to happen. So you would check those out, okay, by doing that. All right, let's go on to this one. Now, you might want to write down this graph. So I just jotted this graph. You just sketch it real quick. It doesn't have to be anything fancy. But here's where we're going to start getting into infinity. Okay, here's where we're going to start getting into infinity now. Okay, so this is an actual function. I don't remember now what I got on this one, but this is an actual function. It would be a rational. It would have a polynomial on top and have another polynomial on the bottom. We're going to get into some of those here in a little bit. But I think if I just gave you this picture, I think you should be able to answer these limit questions for me. Okay, and I just kind of scattered them around the page. I'm going to actually start down here on the bottom ones. But I've got a horizontal asymptote in there. I've got a vertical asymptote in there. Now remember, it is okay to cross. It is okay. Matter of fact, I'm even going to change that. It is okay to cross it's way too big. It is perfectly okay to cross a horizontal asymptote. You can have a graph come up here and go and then level off right at that asymptote. It's okay to cross a horizontal asymptote. It's not a problem, okay? Because remember, a vertical asymptote you would never cross because a vertical asymptote is where the function's undefined, and so you can't have an output there. But a horizontal asymptote doesn't have anything to do with the function being undefined, as you're going to see today. So we get that mixed up because we think asymptote means it can't cross it, and that's not true. Asymptote means that it approaches that, okay? Now, it so happens that a vertical asymptote you're not going to cross because the whole reason a vertical asymptote is there is because of the fact that it's undefined there. And if you ever did cross, you couldn't come back and approach it, or you would fail the vertical line test, right? So you can't do that. But this one, you can go up and down and up and down. Okay? All right, so anyway, just to prove a point there, we could have that. Most functions don't do that. Okay, most functions don't cross it, but, okay. All right, I can think of a real famous sine graph that does that, though. It actually goes up down, but then the humps start getting smaller and smaller and smaller. And it just keeps doing that, and just keeps doing that, just keeps doing that. So basically the x-axis is a horizontal asymptote because it's approaching that as it gets way out there. It's approaching zero. But it just keeps going back and forth, but getting smaller and smaller and smaller all the way. So that's still a horizontal asymptote. Okay? All right, anyway, what's the limit as x approaches 1 on this one? As x approaches 1, the cars meet at 1/2. Right? What's the limit as x approaches -1? Does not exist, but now from now on that is not good enough. We've got to check -1 from the left, and we've got to check -1, and you don't have to rewrite the whole thing out. If you just write this, I'm okay with that. Okay? What's the limit as you do -1 from the left? That's what we're going to write. We're just going to write positive infinity. You can just write infinity, same, because that's where the car is going. On the left, that car is going to infinity. And what about -1 from the right? Negative infinity. And that has to be part of our answer. We're showing that the cars don't meet. So it does not exist. And we're putting from the left and from the right. So we got to show. Yeah. From the right, as you come towards this from the right, what's the car doing? It's going down here to negative infinity. Huh? As you approach from the left, the car is going to positive infinity. Okay? All right, now this is a new concept for us. We can actually put down here as x is approaching infinity. Now what that means is, what is the car? Now there's only one car here. You can't come on both sides of infinity, right? X can't approach infinity from both sides. We're just talking about x going out to infinity. So now we're just one car, right? So the car that's going way out here, what's it approaching? 1. So the car way out here, as you go way, way out here, your y values are getting closer and closer to 1. And so we say that is 1. So whenever you do x, and we're going to talk about this here in a little bit, but x approaching infinity is all about horizontal asymptotes. That's where horizontal asymptotes come in. Vertical asymptotes are all about when you have a 0 on the bottom, right? Vertical asymptotes are 0 on the bottom. Horizontal asymptotes aren't about undefined. Nothing's undefined with a horizontal asymptote. It's all about x approaching infinity. What's happening way, way out here. And then, of course, what about negative infinity? Well, that's this car going way out here. What's he doing? He's approaching 1. Now, it's possible to have different, out here it could be approaching something else, and over here it approach 1, and over here it could approach -1, right? It's possible that they wouldn't be the same. But that would be approaches 1. Okay? Also, because this car is coming down here and getting closer and closer and closer and closer to 1 all the way up here. Now it's a little bit above 1, and here it's a little bit below 1, and in this example, they'd be approaching 0 from above and below. But it's getting closer and closer. It's just going bouncing back and forth. And sometimes it is 0, but we don't care about that. We're saying as you go out towards infinity, it's getting closer and closer and closer to 0. Remember, limits are all about approaching. We don't care what happens at that point. Limit as x approaches 1. We say as it approaches 1, the outputs are approaching 1/2. That's why we did those tables. Remember those tables? It'd say 0.4999999 and 0.50001. Remember the tables? We would look on both sides. It's getting closer and closer. Even though it may never equal 1/2 here, we don't care. It's what it's approaching. All right. And yes, we do put an equals there. It equals 1/2, but we're not saying the function equals 1/2 there. We're saying that it's approaching. All right. What about this picture? Let's look at this picture. Okay, this is another function. Got a vertical asymptote, got a horizontal asymptote there too. Okay? So what would you say as x approaches 3? What would you say on that one? Do the cars meet? No. So we have to say more. We have to say, okay, what's 3 on the left and what's 3 on the right? 3 on the left is going to infinity. 3 on the right, also infinity. Now this is how I want to write it. Now, there are some books, Emily, you look bothered by that. You okay with that?
Yeah.
From the left of 3, the car is going to infinity. On the right of 3, going to infinity. Now there are some books that will let you get away with this. I've seen this written, where they just say equals infinity. I don't like that, because infinity is not a number. And a limit is supposed to equal a number. If a limit exists, it equals a number. Infinity is not a number. What this is really saying, what they're doing, it's kind of like that sine square. It's kind of like a shortcut notation. We're saying, hey, the limit doesn't exist, but both cars are going to infinity. I don't want to do that, right? I don't want to do that because I think that just confuses the issue. Limits have to equal a number. If they don't equal a number, they do not exist. And then we'll tell the story about what's happening on the left and the right. The left, it's going to infinity. On the right, it's going to infinity, just being a habit of doing it. Okay, what about limit as x goes to infinity? Now you're talking about this car out here. As x goes out to infinity, that car is getting closer and closer to 2. What about negative infinity? Also 2. That's getting closer and closer to 2. Okay, so there's your answer. Okay, all right. And finally, this picture. Okay, that red line is what we talked about with the differential equations. That is called a slant or an oblique asymptote. Okay, so what would we say on limit as x approaches 0? Does not exist. Now we would tell the story 0 from the left and 0 from the right. 0 from the left is going, this car is going up to positive infinity. Car on the right, negative infinity. And we would add that to our answer of does not exist. We're telling why it doesn't exist. Why don't the cars don't meet? Because the car on the left is going here, the car on the right is going here. They're not coming in towards a number, so the limit does not exist. What about as x goes to infinity? Where's this car going? Well, to infinity. It's not it, right? A horizontal asymptote, it's approaching a number. This is approaching this line, but its y values are just going to keep getting bigger and bigger and bigger. So what should we say, though? Does not exist. Infinity is not a number, so you can't have infinity as your answer. You either have to have a number answer or does not exist. Now, we also say infinity on that one. Now, see, we can't do the left and the right, so let's talk about this a minute. Okay, so now we say, now wait a minute, we said if it does not exist, we got to say why don't the cars meet? But remember, we're doing it now as x approaches infinity, right? So there isn't a left and a right when x is approaching infinity. There's only the right. I mean, there's only one car. And where's that car going? Well, if it doesn't approach a number, tell me what it's doing, right? If you're saying it does not exist, you're telling me the car out here doesn't approach a number. Well, what is it approaching? Infinity. So we put does not exist and we put infinity. We don't have to put a left and a right because there is no left and right when it comes to infinity. All right, what about here? What's the car going to when x goes to negative infinity? It's going to negative infinity, right? These y values are just going down, 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 down forever and ever. And it's going, so it does not exist. And negative infinity is our answer. Okay? All right, so this is how it works. So a limit will always have a number answer, or it will be does not exist. If it's a number answer, it's where the cars are meeting. Or it's a horizontal asymptote, and it's where that car way out here to the right is approaching, or the car way over to the left is approaching. That's if you get a number. If it does not exist, it means the cars don't meet, or it means the car out to the right that's going to infinity, it is just going out of sight, going to infinity. It's not approaching a number, it's just going to infinity. The car on the left is going to infinity. Okay? All right. So if we can always come back to these graphical examples, I think it'll be helpful. Okay? Because we're going to be looking at a lot of these. Okay, so this you probably want to write down for sure. Now the black part is the stuff we knew before. The black stuff is the part we knew before. And that was, okay, if I do the limit as x approaches a, then I'm either going to get a number. Now, I mean when we substitute in, right? If I plug in an a, we're going to get a number. That means the limit exists, right? And we're done, right? We substitute in, we get a number, bingo, we're done. The big one was we would get 0 over 0. You guys remember that? Right? We would get 0 over 0. And that basically meant keep going. It might exist. The limit might exist. Typically what that means, and I'm going to add that in here, typically that means there's a hole. Now I don't know that I want to say always a hole, but typically that means there's a hole in the graph. And so a lot of times with a hole in the graph, that it's going to exist. Okay, that the cars will still meet. But not always, because sometimes we keep going and then we get a vertical asymptote or something. So that's where we did our algebra, right? We did some factoring, we did a least common denominator, we did a conjugate, right? Now, you still could do those things. So in our next quiz, you might do those things. Least common denominator, conjugate, factor. However, here's the good news. If you're cringing a little bit at, oh my God, I got to do least common, I got to bow tie again. Oh God, I hate that. Right? If you don't like that, that's what Monday's going to be about. That's why it's in chapter 4, the derivative. There's something we can do with the derivative. If you get 0 over 0, the derivative can save the day and make it a lot easier and not have to do some of those algebra things. Okay, kind of interesting how the derivative gets involved here. It's kind of, you look at this, you think, how's a rate going to get involved? How's a rate of change going to affect these derivative limits? That seems strange. Okay, well, it does. It's pretty cool. All right, so that's 0 over 0. And then the other thing that can happen to you is you get a number over 0. Now everybody always asks, what if you get a 0 over a number? What if you get 0 over 4? That's just 0. That's a number. That's part A. That's number 1 up here, right? You get 0 over number, that's just a number. 0 over 0 is this weird one. If you get a number over 0, that always means vertical asymptote. A number over 0 means vertical asymptote. So 7 over 0, 2 over 0, negative 3 over 0. If you get that when you substitute in, you know you got a vertical asymptote. So right away, now here's what we said last time. Remember, we said, well, that does not exist, right? So we would just, if you get 7 over 0, boom, does not exist. But that's now the new thing in blue is we now got to check both sides. Okay? So if it does not exist, if we get 7 over 0, we know it doesn't exist. We know we got a vertical asymptote. Think back to these pictures. If you have a vertical asymptote, you check both sides. Right? You check both sides right here. Vertical asymptote, check both sides. Vertical asymptote right here, check both sides. Right? Okay? So that's what we got to do. Check both sides. All right, the new thing now over here is when we do the limit as x approaches infinity. Well, one of two things is going to happen. And again, these are horizontal asymptotes we're talking about now. So x approaches infinity, x gets really big, way out to the right or the left, either way. You're either going to get a number, which means a limit exists and it's a horizontal asymptote, or it doesn't exist, like this one, right? It doesn't exist, and you got infinity or negative infinity, right? The only way a horizontal asymptote isn't going to, or x approaches infinity isn't going to exist is if way out here it just goes up, 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 or down, 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 down. But if it levels off, then we have a limit on our horizontal asymptote. Okay, so that's the whole picture as far as how infinity can be involved with limits. Now what we have to work on is how do we deal with this with equations like this. Okay? All right. So here's what we're going to do. We're going to go through this one, then we're going to watch this video. I'm going to kind of preempt that video. Remember the video with the diner and stuff? We're going to watch one of those. All right. So if we get this one, right? If we have problem number 1, okay, that says limits involving infinity. So you look at this, you think, well, how does that involve infinity? Huh. Well, what do you do first? What's your first spot? Plug in a 3. So what do you get? 2 times 3 plus 5 over 3 minus 3, you get what? 11 over 0. Okay, so what did we just say on the other page?
You get a number over 0.
So we know we have a vertical asymptote. We say the limit does not exist. And we have to check both sides. Now, here's the problem. It's easy to check both sides on a graph. How do you check both sides on an equation? Pick a number close to 3 on the left and a number close to 3 on the right. Now, this is going to be no calculus. What's a number close to 3 on the left? 2.99999, right? God, how am I going to do that without a calculator? Well, turns out it's actually pretty easy. So here's what you do. So we're going to go back here and we're going to put in so here's what I'm going to say. I'm going to say, okay, number on the left, that'd be like 2.999. And this would be like 3.001, right? 3 on the left, 3 on the right. Now I'm going to plug those in here. Now, what's 2 times 2.999? 5.9999, or whatever. In other words, a number really close to 3 times 2 is going to be a number really close to 6. It turns out on the top, it doesn't really matter, but watch what we get. So if you take 2 times 2.999, that's like 5.999. Plus 5 is like 10.999. Right? Instead of 11, it's like 10.999. It's basically 11, and it's not going to matter, right? Maybe it's 10.998. I don't know. Whatever. It doesn't matter. Here's where it matters. What's 2.999 minus 3? Negative 0.001 or whatever. Now, what if we'd have picked a number closer to 3? What if we'd have picked 2.9999999? This would be negative 0.001, right? A lot of times I don't even put negative 0.001. What I do is I just write down small negative. It's going to be a really tiny negative. What do you get when you divide by 1/1,000,000th? A really big number, right? So what we've got is and this is why this number didn't matter. 10.999 or 11 or whatever that number is. It's positive though, divided by a really small negative. What's that? Big negative. Well, what big negative are we talking about? Infinity. We're talking about negative infinity. So on this side, it's going to negative infinity is what we just learned. It's going to look like this every time. There's going to be a number on top that we don't really care. We do care if it's positive or negative, though. And then the bottom's either going to be a really small positive or a really small negative, right? Because we're picking a number. Remember, we got 0 on the bottom before. So when we put in a 3. So if we put in something close to a 3, we're going to get something close to 0. You see what I mean? We're going to get something really small there. It's going to work this way every time. So if I put 3.001 in here, what's 2 times 3.001? It's like 6.001, right? And then plus 5, it's going to be like 11.001. A lot of times I only just write 11 up there. I don't even care if it's 11.01 or 10.999. It doesn't matter. What matters is the bottom. 3.001 minus 3 is what? 0.001, or what I often do is I just say, hey, that's a really small positive. So you take 11 times 1/1,000,000th, or divided by 1/1,000,000, that's like 11 million, right? So you take 11 divided by a really small positive, you get a really big positive. It goes to infinity. So that's the work I would want you to show right there. But it's basically the same thing we were doing over here, where we were looking on both sides. We're looking on both sides. By a graph, it's easy. You can just see it going to infinity. But on the equation, you actually have to plug numbers in to get that. Okay, so there you go. So we got on the left, it's going down, and on the right, it's going up, right? That's what we got going on with this equation if we were going to graph. We got a vertical asymptote. You would expect to get infinity. Think about it. If you have a vertical asymptote, what do you got? You got infinity going on, right? So you'd expect to be getting infinity over here. All right. So that's one thing that could happen to you with a vertical asymptote problem. Okay? So in chapter 2, we just stopped right here, said does not exist. Now we're moving on and we're saying, okay, now we gotta check the left as well. All right, what about this one? As x approaches infinity. As x approaches infinity. Now, this is a new thing. So this is as x gets really, really big. As x gets really, really big, what is this doing? Okay, so this is new. This is new. Okay, now we know it's going to be that horizontal asymptote. We're talking about way out here, right? As x approaches infinity, we're talking about way out here. Okay, if it was negative infinity, it'd be way down here. Okay, way to the left. But so, again, let's plug in numbers. Now, I know we can't plug in infinity, but we can take really big numbers. So what's 2 times a billion? 2 billion plus 5. 2 billion 5. Now here's what I'm thinking. If I got $2 billion in my pocket, right? I got $2 billion. And it's cold outside, and I'm walking to my car. And a $5 bill goes flying in front of me. Am I gonna chase it? Or am I just gonna get in my car and turn the heater on and give one? Yeah, burn some of my $1 million bills here and whatever, because I don't even care. What's 2 billion plus 5, right? I don't even care. And billion, and to be honest, we're talking about infinity. Is billion even very big? Billion isn't even very big, right? Billion is not big. Time is it? 9. Okay. We got it. Get your time real quick. You ever done this experiment? How big is a million? Let's say you had $1 million and you were going to spend one every second. You're going to spend one every second. Now you have to control it because we're going to need decimals. So get your calculator. Let's say you had $1 million and you're going to spend $1 every second. So that's 1 million seconds. How long is 1 million seconds? How long would your $1 million last? So let's do a million, which is 6 zeros. And we want to, what is 1 million seconds? Well, let's divide that by 60 and see how many minutes. So divide by 60 and control enter. Okay, so that's minutes. Let's divide that by 60 and see how many hours. We're not even going to sleep, right? We're going to spend $1 a second right through the night. So let's divide by 24 and let's see how many days. 11 and a half days. My $1 million will be gone in 11 and a half days. Now let's say I had $1 billion. Now what's $1 billion? How many zeros? 9 zeros. So put in a billion, 9 zeros. And let's divide by 60. And let's divide by 60. And let's divide by 24. Oh, it just added 3 zeros to our answer. That was stupid, right? We should have seen that coming, right? Is it? Oh, it's 11,000 days? Now divide that by 365. Let's see how many years it is. 31 years. Look at that. So you ever think about that? You hear about a millionaire and a billionaire, and don't you think that kind of the same thing? I mean, he's a millionaire, and they got a lot of money. But look at that. A millionaire's money would be gone in 11 and a half days. A billionaire could do the same thing, and his money would be gone in 31 years. See the difference? When you hear about the national debt, they talk about trillions. Let's add 3 zeros onto that. So times that by 1,000. A trillionaire would take 31,000 years to get rid of his money. You see what I'm saying? A billion isn't even that big a number when you compare it to a trillion. And if you add 3 more zeros, and then you got a whatever that number is, quadrillion, or I don't know what is after a trillion, right? Think how much, now you're not 31,000 years, you're 31 million years, right? I mean, you know what I mean? And yet that's not even that big. That's only 12 zeros. Right? No. A trillion is 9, yeah. A trillion is only 9 zeros. You heard of a Google? What's a Google? No, a billion is not. A trillion is 12. That's 31,000 years it would take to spend that money, right? If you're a trillion. Okay? That's only 9 zeros. 12 zeros, 12 zeros, 12 zeros. You heard of a Google? 100 zeros. And we just went from we went from 6 zeros to 9 zeros to 12 zeros. Look what a difference it made. If you had 100 zeros, oh my God, you ever heard of a Googleplex? That's a Google of zeros. I mean, you can't even pick, you just can't even imagine the size of this number. So my point is this. If I'm a billionaire and I see $5, the 5 is meaningless to a billion. I mean, 2 billion and 5 versus 2 billion. But if it's 2 trillion and 5, the 5 is really meaningless. My point is this. As x gets really big, the top of this is essentially 2x. Right? And as x gets really big, what's the bottom here? Essentially x. And how does that simplify? 2. There's the limit on that one. As x gets really big, what you do is you look at the size of the top, especially in fractions. You look at the size of the top and the size of the bottom, and the stuff that's kind of meaningless just kind of goes away. All right, what about negative infinity? Well, it's going to be the same thing. Negative 2 billion plus 5, the 5 is basically meaningless. So 2x over x, and we get 2.
It would take, for Google, it 3.17 even 94
years. Yeah, I mean, I don't even, times 10 to the 94th, that doesn't even make sense to me. There's no grasp of the number. I mean, it's so much longer than they, probably they think the universe has been alive.
Roy told us if you wrote out a Googleplex, you could write out the amount of zeros would go across the universe.
Just the amount of zeros.
Yeah.
Yeah, it's a Google of zeros, right? Yeah. No, yeah, it's just mind-boggling what that number means. Okay, moving on. There's everybody's grades. Do that, sorry. All right, let's take a listen at this.
In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you put in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Now remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3, because when we plug 3 into f, we got a constant divided by 0. Now by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity. Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards a height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger, f gets closer to 2. Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height.
So again, when you have a graph, when they put the graph up there, that's easy to see. When you don't have the graph, we want to be able to get these limits as well.
When I was explaining the last example, I said that x was getting infinitely large, and we translated that mathematically as the limit as x approaches infinity. Now this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. That's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the numerator and the denominator of the given function. By the way, the degree is the highest exponent. So if we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, if we don't write a power, it's inferred to be 1. Now in this case, the degrees of both the top and the bottom of the fraction are equal, and therefore the limit at infinity of this fraction is going to simply be the coefficient attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1, and we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. What happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist because it's infinity.
Okay, so he said a lot really fast there, but basically what we said, he said take the highest power, because as x gets big, the highest power dominates, right? 1,000,000 squared is going to be a lot bigger than 1,000,000, right? And that's what's weird, but if I had $1,000,000 squared dollars in my pocket and there was $1,000,000 bill sitting there, would I even pick it up? And the answer is, well, probably would, but you know, but maybe not, because 1,000,000 squared is 12 zeros, right? 1,000,000 squared, 1,000,000 is 6 zeros, 1,000,000 squared is 12 zeros. Remember 12 zeros? 12 zeros was 31,000 years to spend it on, compared to 1,000,000, which was 11 days, right? 1,000,000 squared would take me 31,000 years to spend $1 a second. 1,000,000 would take 11 days. So 1,000,000 squared is so big compared to 1,000,000 that I'm not going to bother, right? So x squared matters in that, and x doesn't matter. That's what he's saying. You take the highest power. If the powers match, then they're just going to cancel. So we had 2x over x, right? The x's cancel. If they don't match, they won't all cancel, and then you'll get this, and I'll show you here in a second. You don't have to memorize
In
it.
conclusion, if the limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote
See, I don't like
at
writing
x
that. We're
equals
going to write
c.
does not exist, and then we'll check the
Whereas, if the limit as x approaches infinity of f of x equals d, then f has a horizontal asymptote at y equals d. One word of caution. When we say that a limit equals infinity, we're actually saying that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.
Exactly. See, there's a skull and crossbones and everything there. Dangerous, dangerous. Okay. So anyway, so that is the idea there. And let's play out that part that he talked about right there at the end with the degrees being higher. Okay. So here would be 3 quick examples. Okay. Here would be 3 quick examples. I got limit as x goes to infinity on here. All right. And so I've got, all right, on the first one, the high power is a cube. So if x goes to infinity, right? Limit, you can't plug in an infinity. I mean, you could think to yourself infinity cubed, right? Because I was telling Jesse, right, infinity's not a number. We kind of treat it like a number. We got to keep in mind it's not a number. But if I do infinity cubed, right, a really big number cubed, that is so much bigger than x squared, right? Because 1,000,000 cubed, right? 6 zeros cubed, that's going to be 18 zeros. 18 zeros is so much bigger than 12 zeros, right? I mean, that's not only 31,000 years, that'd be like 31 billion years, right? It'd be another 6 zeros on top of 31,000. So it would be, so the cubed is so much higher than the other ones that they're the only ones that matter. So what he said is, you basically, the high powers dominate, you can ignore pretty much everything else, and so you get 1/2. right? Now, what does that mean? That means as this graph comes down, it's going to be approaching 1/2. We have a horizontal asymptote. As x goes way, way out here, it's going to be horizontal. Now, what if that's at negative infinity? Same thing. Because your cube would be big negative, this would be big negative, negative divided by negative would be positive, so it'd still be 1/2. Okay? So when the powers are equal, you just take those coefficients of the high powers and you got it. Now, when the powers aren't equal, you got to think, there's several ways to think about it. What I usually do is I just say the high powers dominate. So the way I do this one is I just say 3x cubed over 4x squared and nothing else matters. The high power on top is the one that matters. When I'm talking about when x gets big now. If this said if x goes to 2, we wouldn't be doing this, right? If x approached 2, we'd be plugging in a 2. But if x is getting really big, then x cubed's all that matters, 4x squared's all that matters. Well, what happens here? We end up with 3x over 4. Well, what happens as x gets really big to this? It's just getting really big. I mean, 3 billion over 4. It's going to infinity. Well, if you think about it, what they were saying is that the high power is on top. If the numerator power is higher, that means the top is going to keep getting much bigger than the bottom. Well, if you have a fraction where the top is getting way big and the bottom's not getting as big, that number is going to keep getting big, right? That's how fractions work. And then the reverse of that would be true here. Now, again, I sometimes will just take the high powers and do this, but you don't have to, right? This will be 2 over 3x. Now, what happens to that as x gets really big? If the bottom gets really big, that's getting really small. It's getting closer and closer to 0. And that's what they said really fast right there at the end. They said that, but you don't have to memorize that. You can just reason it out. You say, well, geez, if the high power, if this is getting a lot bigger than this, the bottom's getting bigger on a fraction. The fraction's getting small, going towards 0. So you're either going to get a number when they're equal coefficients, or you get a number here. That'd be the x-axis, right? So the x-axis would be your horizontal asymptote on that. And then this would be, it's just going out to infinity. Now, we should say does not exist here, too, right? We should always throw does not exist on there on that one, because it's got to be a number, right? Your answer's got to be a number for a limit. If it's not a number, it does not exist, right? If it's not a number, and then we do that. Okay? So that's how we can do those problems without having to see their graphs. Now, the problem is not all functions are going to be just x squareds and x cubes and stuff. Okay? You're going to get this kind of stuff. Okay? So let's look at these two problems. But it's the same thought process. It's the same thought process. You're still saying to yourself, what is happening as x gets really big? Right? Well, what happens, so what's going to happen to e to the 3x? Well, that's going to be e to a really big number. Well, what's that going to be? Well, it's going to be a really big number, right? Now, what about e to the negative x? That's actually 1 over e to the x. That's going to get really small, because e to the x is going to get really big, but it's on the bottom. So this whole thing is just going to go to 0. So this is going to end up being e to the 3x over 4e to the 3x. Does that make sense? Now let me stop here just for a second. Let me stop here just for a second. Because sometimes people run into this, and I gotta nip this in the bud. Does 0 over 0 equal 1? Does infinity over infinity equal 1? No. 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 See, because here's what some people think. Some people will look at this and say, well, this is going to infinity on top. And this is going to infinity on the bottom. So infinity over infinity is 1. No. No. It has to do with how fast they're going to infinity. Isn't the bottom here always going to be what? 4 times bigger than the top. There's no way that's going towards 1. It's actually going towards what? 1/4. Right? It has to do with how fast the top and the bottom are changing. Oh, wait. Are you telling me it has to do with the rate of change of the top and the bottom? Right? Very good change. Remember I said the derivative's going to get involved, it's going to be able to help us on these? Now, I'm going to save that for Monday, so you probably won't even be able to sleep this weekend with anticipation. But, all right, so you're going to cancel those two things out, and you got 1/4 is your answer, okay? What about this one? What is happening, what is sine doing as x goes to infinity, as x gets really big? It's just going back and forth from -1 to 1, right? Just bouncing back and forth, right? As x goes out to infinity, sine is just right? I'm just getting numbers from -1 to 1, okay? So I'm not sure what's going on with that. I'm just going to write that down. What's happening down here? So what's happening with this? What's just numbers between -1 and 1 divided by bigger and bigger and bigger numbers? It's getting really small. Now, it's bouncing back and forth between negative really small and positive really small. Remember that graph I showed you earlier? The one that's just getting littler and littler and littler and just kind of going down closer to the x-axis, back and forth? That's what this would be doing. That's what this would be doing. Because the top's going to alternate between negative and positive, and then you're going to divide by this big positive, right? It's going to get smaller and smaller, but it's going to be negative then positive, negative then positive, negative then positive. It gets smaller, 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 smaller. So there's still a horizontal asymptote right there at 0. On this one, there's going to be a horizontal asymptote right there at 1/4. Right? If you graphed it, looked out there for it, that's what you would see. Okay? All right. So let's look at a couple more problems here. Okay, so now I'm back to this. I'm back to x is approaching 2. Right? I'm not infinity anymore. We're not talking high powers dominate. Right? We're not talking any of that stuff anymore. We're back to regular old limit problems. Okay? So now we plug a 2 into here. Okay, so so let me stop a second. So at this point, I think that's it. Right? For new stuff. Probably for today. I mean, there's going to be some issues, there's going to be some questions you're going to have, there's some things you're going to crop up, and you're not going to quite know how to handle it, but we've talked about everything you really need to think about in handling these, okay? But we just got practice in it. So now, what's the first thing you would do on this problem? You plug in a 2, and you get 0 over, now what did that mean, 0 over 0? 0, 0, no. 0 over 0 meant keep going. Now, we actually have a name for that. We'll write it on Monday. It's called indeterminate. But it means keep going. Well, what can you do on this one? You can factor the bottom. And you get x plus 2, x minus 2. Cancel the x minus 2's. Now what? Now you can plug a 2 back in. Right? 2 plus 2 is 4. You get 1/4. There's a hole. There's a hole at 1/4. Right? So the cars meet right there at 1/4. So now we're just back to, okay, now let's just talk about any kind of limit problems and see if we can handle them. So now we're back to the ones we did before. We got to be able to do those two, right? There's a lot thrown at you, so you just got to think on each one what's going on. Okay, now let's put a -2 in. Now let's put a -2 in. What do you get? -4 over 0. Oh, what did we say to do on that? That's a vertical asymptote. You don't have to write that, but I do just to remind myself. It's a vertical asymptote, which means we probably have some sort of infinity thing going on, right? When you have a vertical asymptote, that's what's happening. Okay, and what do we say you have to do? You have to check the left, and you have to check the right. Okay, now let's check the left. What's to the left of -2? And -1.999 would be to the right. Correct? So we got to check the left and the right. So we get -4 over 0. We say does not exist. Now we got to check these. So let's put in -2.001. Now, let's put it in the top first. What's -2.001 minus 2? Yeah, and I don't really care. I can just call it -4, but whatever. But here's where I care. What's -2.001 squared? Positive I don't know, 4.01, right? A little more than 4, right? Because you're a little more than 2, you square it, it's a little more than 4. So a little more than 4 minus 4 is going to be a really small positive, right? Be a really small positive. And then, so you take negative 4 divided by a really small positive, what do you got? You got negative infinity, right? You're dividing by 1 billionth, you're going to get like negative 4 billion, right? You get negative infinity. Okay, let's put negative 1.999 in there and square it. What do you get? Don't you get like 3.999? Remember, it's a little under 2. It's negative 2, we're squaring it, so I don't care, we'll turn positive. But it's a little under 2, and you square it, it's a little under 4. So it's 3.999, take away 4. And then up here, what do we got here? Negative 1.999 minus 2, that'd be negative 3.999, right? Whatever. And then this is a really small negative, so negative divided by negative is positive. Now, don't think that just because one turns out negative, the other one's going to turn out positive. Not true. Sometimes they both turn out negative if both of them are going down, or sometimes they both turn out positive. It could happen. Okay, it could happen. All right. So anyway, we have to add that in. So we have to have all of this on one like that. Okay. So and we did one of those earlier, so it shouldn't be a problem. So 0 over 0, we keep going. We can do some algebra, but that is where we're going to add our new thing with the derivative. But this wasn't bad. That was easy. The factoring is easy. Okay. Now, this is going to lead into, and I know we only just have a minute or two, so all I want to do here is I just want to say if these are some special uses. You don't have to write this down because we'll start with this on Monday. But back to what you said about infinity and a number, right? Being a number. We wouldn't usually write 1 over infinity, right? But because not a number, but it's like 1 over a really big number. What's 1 over a really big number? Really small number. So it's not unheard of to write that. To think when you see 1 over infinity, you say that's 0. That's not equals. I shouldn't put equals 0. What we really mean is 1 over a really big number is a really, really small number, getting close to 0. Okay, what's 3 times infinity? It's infinity, right? What we're saying is 3 times a really big number is a really big number. It's infinity, right? But then you get into this, and now we're not gonna do this, we'll start this next week, but 0 times infinity. Well, you want to say 0, right? 0 times anything is 0. No, 0 times a number is 0, but infinity is not a number. What this is really saying is a really small number times a really big number. Well, what you have is a battle. You have a really small number times a really big number, and there's a battle. Which one's winning? Sometimes a small number wins and it goes to 0. Sometimes a big number wins and it goes to infinity. And sometimes it's kind of a tie and you get a number. And what's the battle? It's how fast the little number is getting little versus how fast the big number is getting big. And that's where derivatives come in, ladies and gentlemen. Just felt like that. All right. So, your homework. Yes, yeah, 3 days. So, guys, it's like a problem a day. Huh? Well, 2 days. I mean, okay. Homework. You do your homework at night. You got Friday night, you got Saturday night, you got Sunday night. That's what I'm saying. You guys at midnight whenever you do your homework. But it's all going to be Sunday. It's going to be Sunday night, I know. About Sunday night at 10. It's going to be like, let's see, did I have homework? Oh, yeah. Yeah, I got cow. I got some cow homework. Yeah. Okay. So anyway, Sunday night at 10. But
You want to do that? You want to do that problem?
I want you to do that problem. And so 9 through 21 were just some limit problems. There's some, they're pretty much all equations. There might be some graphs, but I think they're pretty much all equations like these last ones we've been doing. So basically, doing these things, especially the last half hour that we were doing as we did those limit problems.